Thank you for the introduction and thank you for the invitation, for the opportunity of speaking here today. So today I'll be talking a lot about the group of Hamiltonian diffeomorphisms. We'll basically be focusing on obstructing torsion. All of the results that I'm going to be discussing today are available on a preprint on arXiv, and it's joint work with Igor Shelupin. So just to start, I'd like to fix once and for all M omega a close connected symplectic manifold of dimension 2n. And since we're going to be discussing the group of Hamiltonian diffeomorphisms quite a lot today, I just wanted to recall its definition. So it's the usual story where we start with a one periodic Hamiltonian function. And by means of Hamilton's equation, we obtain a time-dependent vector field. From this time-dependent vector field, we have an induced symplectic isotopy, and its time-one map is what we call a Hamiltonian diffeomorphism. The collection of such maps form a group under composition, and that's a group of Hamiltonian diffeomorphisms that we're interested in. So a little bit about the motivations of why this is an important group in our field. And well, to begin with, if you have a little bit of a physics background, or if you know a little bit about the history of the subject, this group captures all the admissible motions of classical mechanics. Another interesting thing is that at a first approximation, it's a good way to study the group of the symplectomorphisms that are symplectically isotopic to the identity. And here I'll just refer to this group as SIMP0. In the case that the first cohomology of the manifold is trivial, these two groups actually coincide. And finally, there's this striking theorem by Banyaga, who showed that at least in the closed connected setting, the group of Hamiltonian diffeomorphisms determines the symplectic manifold up to a conformal factor for the symplectic form. So like I said at the beginning, we're interested in the following question, asking whether torsion exists in the group of Hamiltonian diffeomorphisms. And by torsion, I mean a non-trivial Hamiltonian diffeomorphism with finite order. And in 2002, there's this famous theorem by Polterovich who showed that when the symplectic manifold is symplectically aspherical, the group of Hamiltonian diffeomorphisms does not admit torsion. And by symplectically aspherical, I just mean that the cohomology of the symplectic form vanishes on the spherical classes. And while this is the only result of this kind in higher dimensions, though in low dimensional topology, there are some obstructions for homologically trivial symplectic finite group actions on certain Calabi-Yau type manifolds. In the first part of our work, we were able to extend this result of Polterovich to the cases that the symplectic manifold was either negative monotone or symplectically Calabi-Yau. So what I mean here is that we were able to obstruct torsion in either of these cases. And just to recall, negative monotone means that the cohomology of the symplectic form is negatively proportional to the first germ class of the tangent bundle over the spherical classes. And symplectically Calabi-Yau just means that the first germ class of the tangent bundle vanishes over the spherical classes. And this theorem, if you add that to it, that of Polterovich, we obtain the following corollary that states that if you have a Hamiltonian torsion, you can find a homotopy class which has both strictly positive symplectic area and strictly positive first germ class valuation. And this points to an interesting connection between Hamiltonian torsion and Conley conjecture. So just to recall, the Conley conjecture states that for a broad class of symplectic manifolds, every Hamiltonian diffeomorphism has infinitely many periodic points. And what Ginsburg and Grell showed was that whenever one could find a counterexample to the Conley conjecture, or well, that is a Hamiltonian diffeomorphism with only finitely many periodic points, this exact same conclusion as that of the corollary, as this corollary is obtained. So what's interesting then is that one can think of Hamiltonian torsion as some sort of a counterexample to the Conley conjecture. But when in reality, it's never a counterexample because, well, it's a map of finite order. So in particular, every point of the manifold is periodic. But this connection at least points to how one could prove such a theorem. The methods are very similar, proving the Conley conjecture and proving this theorem. So a little bit about, I'm just going to say a few words about the proof. But before I begin, I'd just like to say that for most of this article, we have this idea of using the asymptotics of large iterations to study periodic orbits. And it's quite counterintuitive because on the one hand, the dynamics is quite simple, right? We're just studying something that's periodic. But on the other hand, looking at larger and larger iterations gives you some useful information in order to be able to prove these theorems. And just a little bit about the technical aspect of what we do is, well, we try to generalize these action index methods used to prove the Conley conjecture, but instead of isolated fixed points, we now have to look at this notion of generalized fixed points, which are path-connected components of the contractible fixed point set of a Hamiltonian diffeomorphism. And what's important in our context of torsion is that these generalized fixed points have a constant mean index. This is not true in general. So if you just get any path-connected component of a contractible fixed point, you could have a varying mean index. But the fact that this map has torsion forces the mean index to be constant over these path-connected components. And this is crucial in order to be able to think of these generalized fixed points as de facto isolated fixed points and well, allow these methods to generalize. And well, here I just wanted to write at least one definition of the mean index in terms of the Conley-Zender index. This is how one would define it could define it in the non-degenerate setting, and then just extended by the continuity of the underlying homogeneous quasimorphism in the degenerate setting. So back to the proof, right? We're obstructing torsion in the Calabi-Yau case and the negative monotone case. So in the Calabi-Yau case, for each generalized fixed point, here I'm denoting them by F, either the mean index is strictly positive or non-positive. In the case that it is strictly positive, we can find a sequence of iterations such that the Conley-Zender index grows without bound. And when it is non-positive, we can find a sequence of iterations such that the Conley-Zender index is strictly bounded above by n. And here I have quotation marks because, strictly speaking, we're not dealing with the Conley-Zender index per se, because we're in the degenerate setting. We're actually looking at the support of the local Floer homology associated to these generalized fixed points. So what I'm saying here is, in this first bullet point, is that the allowed values for this support just grows without bound, and the second bullet point here, we can bound it above strictly by n. And I like to point out that in order to have this strict bound here, it is important that Hamiltonian torsion is weakly non-degenerate in the sense that the linearization of the Hamiltonian diffeomorphism at each fixed point has at least one eigenvalue that's different from one. And of course, that the mean index is constant over these generalized fixed points. The whole argument relies on this fact. So we conclude by obtaining a contradiction, because on the one hand, the existence of the fundamental class and the PSS isomorphism implies that the Floer homology at grading n is non-trivial, while either of these two implications above here would tell us otherwise. This argument, or a very similar argument, was used by Salman Zender in their 92 paper for the Colóquio conjecture, though in that case, they were dealing with isolated fixed points instead of these generalized fixed points. For the negative monotone case, the proof is a little bit more complicated, but I'll just say a few words. There, we can find a generalized fixed points and a particular sequence of iterations that carries a fundamental class. And with that sequence, and using the triangle inequality satisfied by spectral invariance and the behavior of the mean index under iterations and recappings, we can find a homotopy class which has non-negative area and strictly positive first rank class valuation. And that contradicts the negative monotonicity of the symplectic manifold. This argument is very similar to that used by Ginsberg and Burrell in their Colóquio conjecture paper in the negative monotone setting. And the main difference being that in that case, the fixed points were isolated. And again, we're dealing here with these generalized fixed points. It is clear, however, that, well, non-trivial Hamiltonian torsion does exist. In particular, in the monotone case, you can take the standard sphere and look at any rational rotation about the z-axis. That will already give you an example of non-trivial Hamiltonian torsion. So if we want to say something meaningful about Hamiltonian torsion in the monotone case, we have to look at somewhere else. And there's this idea that Hamiltonian torsion is related to the presence of non-constant J-holomorphic spheres. And this idea can be found in problem 24 in Introduction to Symplectic Topology by Macduff-Salomon. One can say that this idea is inspired by this great theorem by Macduff, which states that a symplectic manifold which admits a non-trivial Hamiltonian S1 action is uniruled in the Gromov-Witten sense. And being uniruled in that sense implies geometrical uniruledness, geometric uniruledness, in the sense that for each omega compatible almost complex structure and each point on the manifold, you have a non-constant J-holomorphic sphere passing through that point. And there's this general rule of thumb that what happens with Hamiltonian S1 actions or even symplectic S1 actions strongly indicates what might be true for in the case of torsion. Though one needs to be a little bit careful with that idea, because there are examples of Hamiltonian torsion which do not embed into an S1 action. But in general, it works. And what we were able to do was to show that in the monotone case, if the group of Hamiltonian diffeomorphism admits torsion, then the manifold is geometrically uniruled. In particular, this would imply that any non-trivial Hamiltonian S1 action would force the manifold to be geometrically uniruled, which of course was already a consequence of the theorem by Macduff. Secondly, we actually prove a little bit more than what's stated in this theorem. We show that certain algebraic counts of holomorphic curves are non-zero, and that's what implies geometric uniruledness. We prove another sort of uniruledness, which implies geometric uniruledness. And well, in this case, the proof is a little bit more involved, so I'll just say some brief words. try to indicate what's used in the proof. And basically the first step relies on showing that for a Hamiltonian diffeomorphism of finite order, the barcode associated to it has no finite bars. And intuitively speaking, what that means is that the Floer complex associated to the Hamiltonian diffeomorphism has no cancellation. And this allows us to think of Hamiltonian torsion as a generalized pseudo-rotation. A pseudo-rotation one can think of as a strong counterexample to the Conley conjecture, in the sense that it has the minimal amount of fixed points required by Arnaud's conjecture. And while the second part of the proof relied on using arguments of Sholukin, Seidel, and Wilkins of, well, for quantum scene rod operations for pseudo-rotations, which were robust enough to apply to our slightly generalized setting, and which allowed us to condense the argument into another mean index type argument, very similar to the proof of the negative monotone no-torsion theorem that we just discussed. If we want to say something about SIM0, so trying to go a little bit beyond the group of Hamiltonian diffeomorphism, especially in the case where the first cohomology is non-trivial, just by looking at some well-known properties of the flux homomorphism, we were able to extract a couple of corollaries straight from the two theorems I just discussed. So in the first corollary, we showed that a symplectic manifold, which is symplectically aspherical, and which either has non-zero Euler characteristic or has a fundamental group with trivial center, then the group of, well, SIM0 will not admit torsion in that case. And I like to remark that having the condition of having non-zero Euler characteristic is essential, because one can consider the symplectic torus, for example, and look at any rational rotation, and that's going to give us an example of SIM0 torsion. But as we know, right, the Euler characteristic of the torus is 0, so that's not covered by corollary 1. And the second corollary shows that if the symplectic manifold is homologically negative monotone and we have SIM0 torsion, then it is necessarily geometrically uniruled. And I have homologically here in bold, just to say that, well, homologically negative monotone is more than just negative monotone. We're asking for the proportionality over all of H2, not only over just the spherical classes. So it remains to say something about the cases that we cannot obstruct torsion. And there's this idea as well that in those cases, there should be some sort of metric rigidity. This was also implicitly discussed in the preamble of problem 24, which was which is in the Macduff introductory Macduff-Salomon introductory book. And there's also this famous theorem of Newman for the continuous case, which states that for a compact manifold with a distance, one can find a C0 neighborhood of the identity, which does not contain any non-trivial finite subgroup of the homeomorphisms of the manifold to itself. So here I just wanted to recall the definition of the C0 distance. And what we did was prove an analog theorem we wanted to, at least in the symplectic setting. So instead of considering the C0 distance, we looked at the Hoffer distance and the spectral norm. So here I just recall what those are. So the Hoffer distance is a distance in the group of Hamiltonian diffeomorphisms, which is calculated by this infimum here over the Hamiltonian functions which generate this composition. And the spectral norm, which is calculated in terms of these spectral invariants, where this infimum is taken over all the Hamiltonian functions which generate phi, is a norm in the group of Hamiltonian diffeomorphisms. And what's important for us to keep in mind is that this norm, the spectral norm, provides a lower bound to the Hoffer distance to the identity of a Hamiltonian diffeomorphism. And we show that, well, when the manifold is monotone and phi is torsion, then for one of its iterations, the spectral norm is bounded below by rho over 3, where rho here is the rationality constant associated to the monotone manifold. Of course, that implies also this lower bound for the Hoffer distance. We actually showed a little bit more than what's stated in the theorem. We, in particular, if D, which is the order of the Hamiltonian diffeomorphism, is a prime number, then this 1/3 multiplying rho here can be replaced by the floor of D over 2 over D, which tends to a half as D tends to infinity. And generally speaking, this lower bound is sharp, as can be seen by rotation of the standard sphere by 2 pi over 3. This is a Hamiltonian diffeomorphism of order 3, and the maximal spectral norm of its iterations is rho over 3, which is precisely the lower bound provided by the theorem. So before I discuss a little bit about the proof, I just wanted to recall the definition of the spectrum of a associated to a Hamiltonian function. And basically, it is the set of critical values of the Hamiltonian action functional, which is associated to the Hamiltonian function H. And well, so the proof relies on two main steps. So the first, we use some technical Morse-Bot orientation arguments so that we can, morally speaking, treat everything as if it were non-degenerate. And well, a byproduct of these orientation arguments, which is not part of the proof, but quite an interesting proposition in itself, is that the orbits of Hamiltonian torsion must be contractible. Recall that we had already shown that the barcode associated to a Hamiltonian diffeomorphism has no finite bars. And what this implies is that every orbit, in some sense, carries a quantum homology class. So what this allows us to do is to use this formula here relating the spectrum of an iteration of a Hamiltonian function to that of itself for the subset of the spectrum given precisely by these carriers. This is we're going to come back to this, so we'll keep this formula in mind. The second part of the proof relied on finding a new invariant of a Hamiltonian diffeomorphism, here denoted by L, which provides a lower bound to the spectral norm, and which grows linearly with the iterations, at least for small values of the spectral norm. And once we found such an invariant, we could then just conclude the proof of this theorem by means of a combinatorial argument. So I'll just spend my last few minutes defining this invariant, which we call the spectral length. So just before I do that, let me define what the essential spectrum is. And basically that is the subset of the full spectrum given by the spectrum invariants, which are associated to all of the non-trivial quantum homology classes of M. So a good way to visualize the essential spectrum is illustrated here. Well, you have here the real line, and these red dashes correspond to the spectrum invariants. And because of the recappings, one can see that this picture is periodic. So we have this sort of cluster structure. And the invariant, the spectral length, is precisely trying to measure the size of this cluster. And so how do we formally define it? Well, we first find the maximal length of a connected component of the real line once we remove these the essential spectrum. So in the case of what's illustrated here, that will be the length of this connected component, which of course is the same as this because of the periodicity, and remove that from rho. So the spectral length associated to a Hamiltonian diffeomorphism phi can be measured simply by looking at the essential spectrum of a Hamiltonian function generating phi, and then subtracting from rho, the rationality constant associated to the manifold, this maximal length of the connected component of R minus the central spectrum. And this is an invariant because of this observation here. Simply because when we have two different Hamiltonian functions which generate the same Hamiltonian diffeomorphisms, then their essential spectrum coincide up to a constant shift. So of course, the length of these connected components won't change just by shifting this picture around. And well, one can then show fairly easily that it satisfies both of these properties. And with that in hand, we can just simply use some combinatorial argument to obtain the conclusion of the theorem to complete the proof. And well, yeah, that's what I have prepared for today. Thank you very much for listening.